All right, well, good morning, good afternoon, good evening, wherever you are. The title of my talk is From Rational Conformal Field Theories to Modular Tensor Categories to nonabelians. So let's begin with some preliminaries. This talk is intended to provide primary source material for a hypothetical historian of science who's interested in those topics. And it will be focused mostly on my work and my role in these developments between 1986 and 1989. So the account will be biased, but this is the only thing that I can speak about with any authority. And that authority can easily be questioned because memory is notoriously unreliable. We'll see some examples of that. And we all have a tendency to inflate our importance, particularly in recollections of past achievements. Moreover, history is fragile. Written documents get lost or destroyed. There are floods, fires, mold, emails get lost or deleted, magnetic tape decays. My own office at Rutgers has been flooded severely 3 times in the last 10 years, and many documents got lost. When I can, I will back things up with documents. On the other hand, a total loss of memory is a loss of identity, as in Alzheimer's patients. And the same is true for the scientific community. So I do commend the organizers for creating this interesting series of history talks. I also thought it would be valuable to take a look backward and reflect on the road traveled. So I thank the organizers for providing me with this opportunity to talk about this, my role in this history. So first I have to begin with some prehistory. And there are actually 2 strands of that prehistory. 2-dimensional conformal field theory and string theory. And as we've seen in the talks this week, those things are very, very closely related. So 4 aspects of 2-dimensional conformal field theory from 80 to 86 I want to recall, beginning with Dan Friedan's thesis, actually from 1980. He was a student of Is. Singer in Berkeley, and he studied the 2-dimensional sigma model. So you have maps from a 2-dimensional Riemann surface to a Riemannian target space. Riemannian manifold is target space. And so the couplings are the metrics on the target space. And he worked out the renormalization group flow for those metrics in a perturbation series. And as we heard from John Carty yesterday, the fixed points of the renormalization group are very important. And so in this case, the fixed points are some kind of version of Einstein's equations. That seems very deep to me. And it leads to the idea that the space of 2-dimensional field theories is some amazing generalization of the space of manifolds. And within that space are special submanifolds, the solutions of Einstein's equations in the case of the space of Riemannian manifolds, and conformal field theories in the case of 2-dimensional field theories. Then, as we've heard, there was this amazing paper of Byelov, Polyakov, and Zamolodchikov in 1983, and they studied systematically the implications of conformal symmetry in 2-dimensional quantum field theory. And a very important aspect of their papers, they separated clearly the that you had different left-moving or holomorphic degrees of freedom and right-moving or anti-holomorphic degrees of freedom. And they exploited the Virasoro symmetry, the left-moving and the right-moving Virasoro symmetry, and systematically studied its consequences. So this is from their paper. They showed how you could really understand correlation functions in a conformal field theory. Here's a 4-point function of primary fields on the plane. Using conformal symmetry, you can map 3 points to 0, 1, and infinity. The 4th point is a complex number x on the complex plane. And they observed that you could factorize in some internal channel. So you have some unknown structure constant c, which they said has to be determined by the bootstrap. And then there was a function a, which is a function of x and x bar, and it is holomorphically factorized between these functions curly f, which they called conformal blocks. And the crucial point is that the curly f's, these conformal blocks, are determined entirely by symmetry, just the symmetry of the Virasoro algebra. So the idea is you organize your space of fields into representations of the conformal algebra. And then they also observed that if the central charge satisfies a very interesting quantization condition, here P over Q is a rational number in lowest terms, and then you can restrict attention to a finite set of primary fields. The operator algebra closes, and you can compute exactly the anomalous dimensions, and all the correlation functions are computed as solutions of linear partial differential equations. So that was just amazing. And then another important development was Friedan and Chu and Schenker imposed unitarity on these models and found the so-called minimal series. Apropos of the fragility of history, I was asking Friedan about his memory of some of aspects of this history, and he wrote a couple of emails, and you can read this one later, but it's very interesting about how some interesting aspect of his project with Chu and Schenker is lost to history because magnetic tapes are now unreadable. Now, back to Belavin, Polyakov, and Zamolodchikov, they had a notion of what they called fusion rules. But for them, the fusion rules were selection rules. They didn't have any algebraic properties. So here is from their paper, a schematic where they introduced the fusion rules, and it's a schematic version of the operator product expansion. That will become important later. Another important development from this time is the Wess-Zumino-Witten model. So Witten was studying anomalies in incredibly fruitful ways in the early 80s, and he was studying in particular something called the Wess-Zumino term, which kind of summarizes the anomalies with respect to some symmetries. And he realized that in the two-dimensional nonlinear signal model, if your target manifold is a group manifold, and you add this Wess-Zumino term with properly dialed coefficients, then in fact you get a conformal field theory, now called the Wess-Zumino-Witten model, or sometimes the Wess-Zumino-Novikov-Witten model. After the BPZ paper, Knizhnik and Zamolodchikov generalized these BPZ methods to models with Lie group symmetry and found again this kind of finite factorization in the Wess-Zumino-Witten model, and also differential equations obeyed by correlation functions, now known as the Knizhnik-Zamolodchikov equations. Also, at that time, Gepner and Witten worked out the Hilbert space on the circle of the Wess-Zumino-Witten model, and it's a very interesting formula. It's a direct sum of what are called the integrable highest weight representations, and so it's a finite sum of, again, holomorphically factorized holomorphic times anti-holomorphic representations of the current algebra symmetry. It's interesting to compare this formula with the Pater-Weyl theorem for the decomposition of the L2 functions of a compact group as a representation of G left times G right, left and right moving actions on left and right moving, I shouldn't call them moving, actions on the left and the right of the group on functions of G. And again, it has this formal property. This is not that surprising, since the Hilbert space of the WZW model are L2 functions on the centrally extended loop group. But a really crucial thing is that in the quantum theory, it's restricted to a finite sum. And also, it made clear that, the Wess-Zumino model is just all about group theory, and in fact, even becomes finite dimensional group theory in the semi-classical limit where K goes to infinity. Finally, and we heard about this yesterday from John Carty, a crucial insight was modular invariance. So in string theory, I think this goes back to Joel Shapiro, where he was studying the dual model. And he told me once that his paper, where he introduced the modular group and the fundamental domain, actually got 0 references for 10 years. But it's a really amazing insight. It played an important role in cancellation of global anomalies in the heterotic string. And as we heard yesterday, it was realized by John Carty that it also plays a very important role just in two-dimensional conformal field theory without any reference to string theory. I remember as a graduate student at the time hearing talks by Werner Nahm, who was also entertaining some similar ideas, but I can't find that he wrote anything. The closest thing I could find is this paper he wrote after the heterotic string paper. Now that brings me to the second part of the prehistory, string theory. So I was a graduate student at Harvard from 82 to 85, and the cool thing to work on at that time was the theory of anomalies. Anomalies have a very complex history. If you have a series of history talks on physics from this time, I recommend a talk on the history of anomalies. And so we were looking at papers like this and the T.S. Singer paper, and most importantly, the paper of Alvarez, Gomez, and Witten on gravitational anomalies, where they noted that in the type 1 superstring, you had in general anomalies, gauge anomalies, and the theory was inconsistent, which motivated Green and Schwartz to have a closer look. And they found, to their astonishment, that there were only two ways you could cancel the anomalies with SO32 or E8 cross E8 gauge group. One of those flashbulb moments I have is of walking into the office of two postdocs, Luis Alvarez Gomez and Paul Ginsberg at Harvard, and hearing about the news from Aspen. This discovery was made at the Aspen Center for Physics in August 1984. That led to a mad dash in the community to try and find a string theory whose gauge group in space-time is E8 cross E8. Peter Freund had some of the right ideas, but the definitive treatment was given by Gross, Harvey, Martinick, and Rome in their formulation of the heterotic string. And there are a lot of great ideas in that paper. It's a huge, significant development. One of the ideas that's particularly relevant to today's story is that they observed that you don't have to have the right-moving CFT be the same as the left-moving CFT. Sometimes you can glue a right-moving to a left-moving CFTs, even if they're different CFTs. So it was a very heady time. There was the famous paper on Calabi-Yau compactification. So that gave us a huge new set of compact Einstein manifolds, therefore a huge new set of conformal field theories. There were also significant developments with the world sheet. For example, an outstanding paper from that genre was Friedan, Martinick, and Schenker. And then everybody was really quite surprised, taken by surprise, when Narain came up with a construction of heterotic string theories in dimensions less than 10. This was interpreted by Narain, Sermati, and Witten as just toroidal compactification of the heterotic string with a flat metric, flat B field, and flat gauge field. And if you look at the partition function on the torus with modular parameter tau, so Q is e to the 2 pi I tau, tau is the conformal parameter of the torus. If you look at the partition function of the relevant conformal field theory, it has an expression like this, where you see a sum of holomorphically factorized terms. Q is holomorphic in the modular parameter, Q bar is anti-holomorphic, but the sum is an infinite sum because the gamma here is an even unimodular lattice embedded into Euclidean space. So this sum is actually known as a Siegel-Narain theta function. The Siegel is for Carl Ludwig Siegel, who was one of the outstanding mathematicians of the 20th century. He was interested in this function for its use in analytic number theory. So for our story today, it's useful to look at the simplest case where the target space is just a circle of radius r, and then the Siegel-Narain theta function becomes a sum over two integers, n and w, and the p left and the p right are just real numbers, which are related to n and w, and the radius r by these famous formulas. So you notice that if r squared is a rational number, then you can solve the equation in the integers n and w. You'd solve the equation p right equals 0, and there'll be infinitely many solutions. And on the other hand, the different solutions lead to different values of p left. So if I fix a power of q bar, there are infinitely many powers of q that go with it. And similarly, the other way around. And so the theta function can be written as a finite sum of holomorphic function times anti-holomorphic function. Those are level n theta functions. So this was noted in 1987 independently by Friedan and Schenker, by myself, by Dijkgraaf, Verlinde, and Verlinde, hereafter known as DVV, and perhaps many others. Now, just a little comment about what was going on at Harvard and string theory in 85 to 86. All the really great stuff was happening at Princeton and Chicago. We kids felt that we really wanted to understand this stuff. We wanted to learn and participate. So despite opposition from the senior faculty, the kids ran the show. The kids being Luis Alvarez Gomez, Stephen and Vincent Della Pietra, Jacques Dissler, Paul Ginsberg, myself, Phil Nelson, Joe Polchinski, and Kumran Vafa. And we were trying to learn about all these great things that were going on at Princeton and Chicago. And we did a lot of our own work on two-dimensional CFT and string theory, mostly from the worldsheet perspective. So in that context, it was a real important development when Bilavin and Knischnik wrote their paper observing that the integrand of the bosonic string, the 26-dimensional bosonic string, is holomorphically factorized. So little m in this formula is a complex modulus on the moduli space of Riemann surfaces of genus G. So we could think of the bosonic string partition function as some kind of inner product on a section of actually a trivial line bundle on the moduli space of curves. Now, before the Bilavin and Knischnik paper came out, I walked into David Mumford's office to explain some of what was going on at the physics department about theta functions, modular forms, integration on moduli spaces of curves, because his magnificent 3-volume series, Tata Lectures on Theta, were enormously helpful to the work of us at Harvard at the time. And I had my one and only discussion with David Mumford was amazing. So during that discussion, he explained to me about the Mumford isomorphism, and I was not too slow to realize that 13 is half of 26. And so I was extremely excited because it was clear this had something profound to say about the bosonic string integrand. And full of excitement, I called Phil Nelson. At the time, he was visiting Joe Polchinski in UT Austin, but we were too late. That day, they had gotten a preprint from Moscow, the Bilavin and Knischnik paper. So there was competition between Harvard and Moscow, but as far as I can remember, it was not at all acrimonious. So that is a little bit by way of prehistory. Now I want to talk about 3 roads to rational conformal field theory. So there were really 3 ways that people arrived at this idea. By far the most influential and well-known is that of Friedan and Schenker. So they wrote a series of 4 papers, of which this is the largest and most influential, called The Analytic Geometry of Two-Dimensional Conformal Field Theory. I asked Daniel what was his motivation, and he said, well, it was a synthesis of BPZ and Cardy. An important observation they made in this paper was that conformal blocks should be thought of geometrically as sections of projectively flat, infinite dimensional vector bundles over the moduli space of curves. For today's talk, it is important that they were thinking about infinite dimensional vector bundles. And then correlation functions for fixed moduli, let's say M and M bar, are then to be thought of as pairings of sections of this vector bundle with a metric, a Hermitian metric, on that bundle. Now, remember that moduli includes positions of punctures. So this includes things like the 4-point function on the plane and all of that. The A and the B are summed over. They label Virasoro conformal primaries. And so generically, the sum is infinite dimensional. For example, if C is greater than or equal to 1. Of course, they were well aware that it would be finite dimensional in the BPZ case. And if you look through all their papers, they're always assuming that the bundle is infinite dimensional, except for one crucial paragraph where they say that the simplest tractable non-trivial examples would be the Gaussian models. So they're referring to that Siegel-Narain theta function at special points in the Siegel and the Narain moduli space, and minimal models. And they didn't quite correctly understand how their infinite dimensional bundle should be related to the finite dimensional bundle, but they understood that it was really important to think about a version of their modular geometry where the bundles are finite dimensional. Now, after that, they continued working, after those papers, they continued working on the subject, and they started speculating that the space of CFTs is an arithmetic variety, and the degenerate points, which are now known as rational conformal field theories, are like the rational points of this variety. And at the same time, they were talking to Peter Freund, who was thinking about p-adic strings and things like that. So we don't know, but most likely Daniel coined the term rational conformal field theory in the summer of '86 or in the '86-'87 school year. So the second route to rational conformal field theory is the route I took. I was at Harvard and the Institute for Advanced Study. Oh yes, that's me. As you can see, at the time, I haven't changed a bit. I was at Harvard and IAS at '86, '87. I was interested in what string theory could say about the cosmological constant problem. You see, at the time, graduate students like me were told that because the cosmological constant is measured to be less than 10 to the minus 120 in natural units, it is obvious that it has to be zero. And it was indeed so obvious to almost everybody that it was just taken as an article of faith that the cosmological constant is zero. Another flashbulb moment is when I was crossing the street at Harvard Square with Steve Weinberg. He told me he didn't think the cosmological constant was zero, and he was writing a review to explain why. I thought he had gone crazy. However, the measured value of the cosmological constant is 10 to the minus 122 in Planck units. Well, you see, it's something with units. If you measure it in milli-electron volts to the fourth power, it's order 1. So that, by the way, to me is one of the most amazing predictions in 20th century physics. It's just an absolute act of genius on Steve Weinberg's part. But we all the rest of us thought that the cosmological constant was zero, and we had to explain why. So in string theory, the cosmological constant is the partition function summed on genus G surfaces. So if you put together the heterotic string idea together with Bielavin and Knizhnik and Friedan and Schenker, you see that the cosmological constant is the inner product of two sections of a projectively flat vector bundle over the moduli space of curves. And so I had an idea, I thought it was a good idea, that maybe the cosmological constant is zero because there's a selection rule. There's some symmetry in psi left and psi right transform in different representations of that symmetry, and it's a pairing that's zero because of a selection rule. So at the Institute for Advanced Study at time, I walked up to Pierre Deline and asked him what he knew about symmetries of moduli spaces. And he told me about Atkin-Lehner symmetry. So if you look at the moduli stack of elliptic curves, there are no holomorphic automorphisms. But if you look at the modular curve for congruent subgroups of the modular group, then there are holomorphic automorphisms because there are elements in PSL2R which normalize those congruent subgroups. So the idea was, okay, let's start with the one loop partition function and just find psi left and psi right, which transform in different representations of an Atkin-Lehner symmetry. Then we have to integrate over the fundamental domain for a congruent subgroup of the modular group. The full modular group is then a finite disjoint union of cosets of that congruent subgroup. So if we let chi I be a basis for the gamma I transforms of psi left and psi right, we get a partition function where the integrand is a finite sum of holomorphic times anti-holomorphic. And so then I was off to find some models that did this. And obvious place to start is asymmetric orbifolds of Noreen compactifications. And my first example was a 2D compactification of the heterotic string, which led to an amazing cancellation that if you integrate with a natural measure, the theta function of the Leach lattice over eta to the 24, you get 0. Well, it was later pointed out to me that this is an easy consequence of integration by parts, but I didn't know that at the time. And so I plotted the cumulative cosmological constant as a function of the mass of the masses of the higher and higher massive particles. And you got this cumulative cosmological constant converging rapidly to zero. So we were all very impressed with that. And I spent a lot of time with very limited success trying to make models. But because of that limited success, I decided really we should focus on what conformal field theories give us partition functions, which are finite sums of holomorphic times anti-holomorphic functions of the moduli. So my first of two papers came out in March 1987. And there's a paragraph in that paper saying, recently, Friedan and Schenker have independently investigated backgrounds of this type and developed a notion of rational conformal field theories, which is probably the first mention of rational conformal field theories in print. The third road to rational conformal field theories is the road from Utrecht. And here is DVV celebrating their 60th birthdays. To my mind, that route really starts from a very important meeting in Cargès in July 14 to 30, 1987. So Dan Friedan was there lecturing about modular geometry. I was there lecturing about Aitken-Lehner symmetry. And Verlinde and Verlinde were there talking about the classification of C=1 conformal field theories. So I had an email exchange recently with Eric Verlinde asking him what his motivations were for some of the work he did that we'll hear about in a moment. And he was saying, it says in this email, you can read it later from the slides, is that he really started with this work at Cargès on C=1. So here's their paper. And eventually that led to Eric Verlinde's famous paper from March 88, where in the abstract, first line of the abstract of Eric's paper says, we study conformal field theories with a finite number of primary fields with respect to some chiral algebra. So Eric's definition is very close to the modern one, that you have an extended chiral algebra, or mathematically a holomorphic vertex operator algebra with finitely many highest weight representations. The germ of that idea is already in the DVV Cargès paper. Here's the relevant part of their paper. So I explained to you before how the Siegel-Narain theta function for the target space being a circle has this interesting property. When the radius squared is a rational number, it can be written as a finite sum of holomorphic times anti-holomorphic level n theta functions. But DVV went further in an important way. They explained why that happens. They said, look, in the spectrum of the theory, there's a chiral operator, just a function of z, which has integer spin. So we can add it to the vertex operator algebra to get another vertex operator algebra. And that new vertex operator algebra has a finite set of representations. So we'll return to Eric's paper later. But before we get there, I want to talk about some events that happened in Princeton in the fall of 1987 and January of 1988. So Peter Goddard provided me with this amazing document, the report for the academic years 1987-88, 1988-89 from the Institute for Advanced Study. And they had an interesting idea at the Institute. They said, let's have the mathematicians and the physicists try to talk to each other about conformal field theory. And so they had a little mini program in the fall where they tried to foster this mathematics physics interaction. And indeed, Friedan and Schenker and Graham Siegel were lecturing. Not only that, they were lecturing back to back. So here are some of the seminars that were happening in that series. And you see that Steve Schenker lectured and then Graham lectured, or Dan Friedan lectured and then Graham lectured. Now, I had discussions with Daniel Friedan, and with those discussions that inspired me to try and prove that rational conformal field theory, defined by this finiteness condition, not by the extended algebra, but by the finiteness condition, to prove that the central charge and the conformal weights in a rational conformal field theory are rational numbers. So back to tea time at the IAS, I remarked to a mathematician, Greg Anderson, that the physicists are interested in flat vector bundles on moduli spaces of curves. And he immediately said, oh, well, you should be studying ordinary differential equations with regular singularities. I was impressed by that, and we started a very nice collaboration where we proved that if you have a modular invariant partition function, which is a finite sum of holomorphic times anti-holomorphic, then if the Q expansion has integer powers, if the Q expansion has integer coefficients, then the exponents determined by the by the central charge and the conformal weights, the exponents have to be also rational numbers. So we proved that C and H are rational. But you can see in this paper that I was confused just the way Friedan and Schenker were confused. We say that we have a degeneracy, we expand the partition function this way in terms of these coefficients, NAB, and we say that's the degeneracy of representations, but frustratingly, we don't say representations of what. And if you take literally what I said, that they're representations determined by H and H bar, that's wrong, because that would be representations of the Virasoro algebra. But on the next page of this paper, we say that NAB is a finite sum. Anyway, if you have this finiteness condition, then you prove that C and H are rational using the method of modular differential equations. And that was taken up in some beautiful work by Mathur, Muki, and Sen. And actually, it continues to be a subject of study to the present day. So Sunil Muki has continued to study this with various collaborators. Another paper from that time is a paper I wrote with Jeff Harvey and Kumran Vafa, where we actually kind of killed the Friedan-Schenker idea that you could always approximate any conformal field theory by rational conformal field theories. We found some isolated conformal field theories which are not approximated by rational ones. And then the final thing that happened in this period, which is really significant, is that on January 5th, 1988, in Jadwin Hall at Princeton University, Eric Verlinde gave an amazing talk on the modular transformations in the fusion rule algebra. I have copies, a Xerox copy of his transparencies. He still has the transparencies. And, this is the first page. And again, quoting Eric, the ideas for this paper really came out of that work of DVV at the Cargès School. His breakthrough came in October '87. So here's another slide from his talk. And what he's doing here is recalling what was done in the DVV Cargès paper. So very importantly, they're studying the Gaussian model. So they think in terms of momenta flowing in various channels, and they introduce operators associated with closed curves on the torus. So we have A cycles and B cycles, and they have operators P of A and P of B, which are supposed to measure the momenta going through that channel in a conformal block for the torus. And they observed that these are related by some kind of canonical transformation, and geometrically, it's obvious that the modular transformation, which exchanges A and B cycles, should exchange these operators. But then the stroke of genius is that this should be extended to all rational conformal field theories in the following way. We observe that the unit operator is the leading term in the OPE of a field with itself. Well, we are assuming the field is self-conjugate, so a field with itself. And so we can stick in the unit operator, then view that as the leading term in an OPE of phi I with itself, pull the operators apart, and then take one around the B cycle and let them re-annihilate. That procedure is nowadays known as a Verlinde operator. So it's some kind of operator on the space of conformal blocks associated with a cycle on the torus. And now, because we have coefficients of an operator and linear operators form an algebra, I forgot to say one important thing. And Verlinde then said, well, the matrix elements of this operator are basically the fusion rules. So now operators form an algebra. So this way, the fusion rules define an algebra. So in BPZ, the fusion rules were just selection rules, but now suddenly they become an algebra. And moreover, from the construction, it's obvious that they're diagonalized by the S matrix. So the next day, we were all kind of dumbstruck by that talk. And the next day, there was an important meeting, the first of 3 in this talk, in Witten's office in D building at the IES. And I don't remember exactly who was there. Certainly Kajdan was there. I was there. I think Nadi was there. And I do remember we were trying to figure out what Eric had said, and Edward Witten kept saying, "This is magic. This is magic." So Eric did release a preliminary version of his paper during his Princeton visit. And I had a crucial discussion with Eric about how in the world would you prove this? And he suggested looking at consistency conditions of 2-point functions on the torus. So his paper came out in March, and it's pretty much the same as what's in the talk and the preliminary paper. Let's see, yes. And so this is a crucial part of the paper. So the A's are the coefficients, the matrix coefficients of these Ferlinda operators, which it's not too hard to show that those can be expressed in terms of the modular S matrix. Then the really big part of the conjecture is to conjecture that those are equal, equation 3.13 here, that those are equal to the fusion rules. So you read the paper, it's elegant, it's readable, it's convincing. But reading it, I am reminded of David Kajdan's quip, which he made years later, is that physics is very interesting. There are many interesting theorems. Unfortunately, there are no definitions. So what was missing from Eric's paper? Well, the key thing, as he noted himself in the paper, is an identification of matrix coefficients of Ferlinda operators with fusion rules. Now, there was a minor glitch in the talk and the preliminary paper preprint where Eric looked at a bunch of examples to confirm his conjecture. And in every example he looked at, the fusion rules came out to be 0 or 1. And Kajdan, amazingly, real insight, Kajdan understood that the fusion rules are really to be thought of as spaces of intertwiners. And then he remarked that, well, okay, if you just look at SU3 and you consider the space of intertwiners from the adjoint tensor the adjoint to the adjoint, that's a more than one-dimensional space. There are F and D symbols. So Eric corrected that in the talk and his paper. But another thing that was missing from his paper is the notion of a chiral vertex operator. So that brings me to the next part of this talk, my work with Seiberg in the spring of 1988 on braiding fusion S and T matrices. So actually that collaboration started with Tom Banks, but then Tom went to California and started working on other things. So it was me and Seiberg. Now, at the time, we knew about the BPZ and the Friedanchuk-Shanker minimal models and unitary classification. We knew from Carty about the constraints of modular invariance. We knew about the C=1 classification of DVV and Paul Ginzburg. There was this amazing result of Capelli, Itzikson, and Zubair on the classification of SU2 WZW models, and then by the GKO construction that gave a classification of the minimal series. And then there was Ferlinda's conjecture. So the time for systematic classification seemed very right. Now, at first, we were just bumbling around, but somebody, I don't remember who, it was either Peter Goddard, Graham Siegel, or Edward, gave me a copy of Tsuchiya Kaniya's paper. And that was really the key step that got us going. So Tsuchiya Kaniya's paper is on vertex operators and conformal field theory on P1 and monodromy representations of the braid group. Here's the first paragraph of their paper. Our aim is to give a rigorous foundations to the work of Konishnik and Zamolodchikov and to reformulate and develop the operator formalism in conformal field theory on the complex projective line. Then look at the next line. The space H is taken to be the sum of integrable highest weight modules of the affine Lie algebra. Now, remember, notice that this is completely chiral, even the Hilbert space. On the other hand, I told you that the Hilbert space of the WZW model on the circle is a finite sum of highest weight representation times its conjugate. So, we thought, well, that can't be right. We didn't really understand about boundary conformal field theory at all at that point. So, but we said, look, this is interesting. And indeed, if you take that chiral Hilbert space, they can define on it what they called chiral vertex operators. So Nadi and I said, aha, this is something really good. And we even adopted this notation, this graphical notation for the chiral vertex operators. And Tsuchiya and Kaniya understood that if I compose two chiral vertex operators and analytically continue carefully Z around W, then there will be some kind of exchange relation or braiding relation. And those would have something to do with the braid group. They also studied fusion, but they ended their paper too soon because what they did is they wrote this diagram, which is important, but then they just wrote a bunch of explicit formula for the connection coefficients for the KZ equation for the SU2WZW case. They didn't introduce a fusion tensor, and so they couldn't study its consistency properties. There was an important follow-up to Tsuchiya and Kaniya by Kono, where he studied the monodromy representations provided by the KZ equations on the plane and its relation to braid group representations. It did not influence me, but it did influence others in the field, Froelich, Siegel, and I should have added Witten here because it certainly influenced Witten too. It did not combine the operations of braiding and fusing or generalize to higher genus. So in February and March and April, I had some really intense discussions with Nadi Seiberg, where we studied consistency conditions of these conformal blocks, and we found polynomial constraints on the braiding, fusion, and modular transformation matrices. And we announced the results in a talk I gave at the Institute on April 22nd. And here's the first slide from my talk. You see the first line is AIM is classification of RCFT. And I think the title of the talk says a lot about our motivation and the influences on us. The title of the talk was Verlinde Magic and Modular Geometry. The magic is a direct reference to that discussion in Witten's office, and modular geometry is reference to Friedan Schenker. So again, from that talk, we introduced the braiding matrices following, slightly modifying the Tsuchiya-Kaniya notation. We introduced these C matrices. They call it, Tsuchiya-Kaniya called them C too. But then importantly, we introduced these fusion matrices. And we defined them in terms of the operator product expansion of these chiral vertex operators. The N here is for Nadi, because Nadi made some particularly smart remark in one of our first discussions on the subject. And then we found the consistency leads to a bunch of polynomial relations on these tensors. And we conjectured that this is the full set of independent identities on all of these tensors. At the time of that talk, we said it's almost proved. So what was the proof? The proof was to build a simplicial complex whose vertices are the dual diagrams and whose edges are generated by these simple moves, by these fusion and braiding and S and T moves. And then, for example, if you just look at fusion, you have some complicated conformal block, basis of conformal blocks like the one here with all the question marks. And you ask yourself, well, supposing I rearrange this in some complicated way, just using the fusion move, then am I going to get other relations besides this 5-term relation, which at the time we called the shield identity? So what we proved is that if you fill in, if you introduce 2 cells into this one complex by filling in all the shields and more generally filling in the hexagons, then you could see that the complex is simply connected. So that was our method of proof. And the talk devoted a lot of space to a proof of the Verlinde conjecture using those relations, which led to the second important meeting in Witten's office in D building. So the day after my IIS seminar, we met with Pierre Deline and maybe also David Kashdan in Witten's office. And I remember clearly Pierre Deline explained to us about tensor categories and the importance of categories. So here I have to step back and talk a little bit about the attitudes of people like myself and well, I don't think I shouldn't speak for Nadi, but the attitudes of myself about categories. I was aware of them, but I had not studied them in any depth. And frankly, I did not take category theory very seriously. I regarded it as overly formal, abstract nonsense with no content. I even generally made fun of category theory, and I have 3 exhibits of that. In 1987, the physicists were developing something called the operator formalism. So the idea was that if you have a puncture with a local coordinate, or equivalently a little disk cut out of a Riemann surface, then you associate a Hilbert space with the circle of that disk. And if you have a bunch of disks, you take the tensor product of the Hilbert spaces. And that idea is certainly there in the Friedan, Martinick, and Schenker paper, and maybe probably lots of other places in the literature at the time. And then Qumran made the observation that, well, if we just glue those disks together, those circles together to make another Riemann surface, then everything works nicely. And I remember when Qumran told me about this idea, I joked with him. I said, "Oh, Qumran, this is nothing. You're just defining a functor." And we both laughed, and that was that. But as we'll see later, that idea, combined with a knowledge of Bordism theory in the hands of Graham Siegel, led to a very profound remark. But we just thought it was a joke. And here's another example where I make some dumb joke about categories in my Cargès write-up. And most other physicists I talked to didn't know about category theory and didn't like it when it was explained to them. My 3rd exhibit comes from that April 22nd talk, where in that talk I introduced a remark which I attributed to Edward Witten, that our shield identity is related to the Birkhoff coherence theorem of category theory. And I'm sure Edward got it right and told me it was the MacLean coherence theorem of category theory. I had some wires crossed, and of course I knew the famous textbook on algebra of Birkhoff and MacLean, and so I somehow got Birkhoff and MacLean mixed up. And that blooper even continued into the preprint, but thankfully was fixed by the time it came to publication. I met Saunders MacLean years later in Cambridge. He sought me out to remind me of this and told me he was very amused by the whole thing. Anyway, after the Deligne and Kazhdan and Witten response to my seminar, we took categories seriously and started studying them. And probably it was Pierre Deligne who told me to study these 2 papers. My French has never been very good. So it was quite a struggle, but in preparing for this talk, I looked through some old notebooks in my office, and there are thick notebooks where I actually was meticulously working through all the commutative diagrams and all of that in those papers. So I was taking it seriously, finally. So here's our paper based on for our work of that spring. There are no categories other than the footnote with the blooper. We sensibly changed the Tsuchiya-Kaniya notation of C to capital B for braiding, which is what it is to this day, and the N for Nadi to F for fusion. And we also, this was just a few weeks after the talk, we turned the almost proved into proved. So this is from our paper. And in order to prove the higher genus relations, we had to form, we needed a formula for the S matrix in terms of the braiding matrix and the conformal weights. Now, I have to say we failed to appreciate the importance and significance of this formula, other than the fact that it allowed us to give projective representations of mapping class groups at all genus, thereby defining a finite dimensional modular geometry in the sense of Friedan and Schenker. So at the time, we had in mind a 3-step classification program for rational conformal field theories. First, you classify solutions to the polynomial equations. In modern language, that means classify modular tensor categories. Then you use the categorical viewpoint to try and imitate Tanakian reconstruction from the category of representations of a group to a group. So the idea was somehow we would construct the chiral theory, and we realized that we would only be able to construct the chiral theory up to tensor product with purely holomorphic conformal field theories. And then you would classify the ways the chiral parts could be glued together, left movers with right movers, to make a full rational conformal field theory. So we tackled the third part first, how to combine left movers and right movers. And that was a paper, Naturality and Conformal Field Theory. And we made the important remark that it should be governed by automorphisms of the fusion rule algebra. Parallel paper of Dijkgraaf and Verlinde made the same remark. Nowadays, we would say you study auto equivalences of the braided fusion category. And again, we wrote this formula for the S matrix and again failed to appreciate the importance and significance. We also introduced more formally this idea of extension of chiral algebras as a way to generate new rational conformal field theories from old ones. So the idea is you add an integer spin holomorphic field to the chiral algebra and only keep fields local with respect to that field. That idea led to this notion of condensation, or anion condensation, which was started by Bice and Slingerland in their study of the spontaneous symmetry breaking of quantum group symmetry. And well, Nadi and I have been very critical of the use of the word condensation, which was initiated by Bice and Slingerland. Nobody listened to us, and so it has become widespread and standard in the field. But again, in preparing for this talk and digging into those, taking out old boxes of notebooks and things and going through the notebooks, I found an unpublished paper of Moore and Seiberg, where we talk about this process of extension of chiral algebras in terms of adding invisible 't Hooft operators, which we say have been condensed. So I have to say that I'm shocked, absolutely shocked, to find that condensation has been going on at the Institute. Now, anion condensation remains a vibrant topic of study to this day. In fact, here at the bottom, you see there was a Simon Center for Geometry and Physics workshop just 2 weeks ago, and there were talks about anion condensation. Some other modern developments related to this is combining left movers and right movers is now understood, and this is probably the right point of view, in terms of the existence of topological defect operators in these papers. But a systematic classification like that of Capellius and Zubair seems out of reach. There is a paper that looks at the autoequivalences of braided fusion categories for, I think, simple affine Lie algebras. Now, in the summer, we also wrote up our short paper into a long paper with all the details of various proofs. And then you see in that paper that we were stressing the role of categories much more. And we were drawing an analogy between a rational conformal field theory data that we had and the data provided by the representation category of a compact group. So that's what you see on the right. On the left, there's another important idea from that paper, which is the proper way of taking a tensor product and thereby interpreting the fusion rules as a space of intertwiners. So you see, the issue is this. If you have representations of the Virasoro algebra of central charge C, and you take the tensor product of two representations, well, in the standard way of doing tensor products in representation theory, you would get a representation of this Virasoro algebra of central charge 2 times C, not C. But we are talking about a conformal field theory with Virasoro algebra with just the central charge C. Now, the ideas of contour deformation and so on allow you to define a different kinds of tensor product, which is what we did. And so we could interpret the fusion rules as dimensions of spaces of intertwiners. We also gave a detailed proof of what we called the completeness theorem, or if you like, the projective representations of the modular groups. And we covered the cases of genus 0 with all punctures, genus 1 with all punctures, and genus G bigger than 1, with 0 punctures. Our method of proof was to take a set of generators and relations and assign matrices associated with those generators, and then check that the relations hold up to a projective factor. We couldn't do it for G with for genus bigger than 1 with punctures because no such presentation was known, at least not to us. So for this, we were severely arraigned 10 years later in an important paper and later book by Bakalov and Kirillov. Actually, in our paper, in our Trieste lectures, we say quite clearly that we couldn't do Gn for G bigger than 1 and all numbers of punctures. There were some parallel developments at the time which we need to take account of. So in August 1987, Graham Siegel introduced for the first time his vision of how a conformal field theory should be defined in terms of a functor from the Bordism category to a linear category. So this, I think, is the first time it appeared in print, and later it became his very famous but unpublished but widely circulated definition of conformal field theory. And this is hugely significant because this is the beginning of the functorial approach to defining quantum field theory. So functors from a Bordism category to some other monoidal category, this is where it all started. And to my mind, it's really one of the most beautiful ways of trying to approach the whole subject of quantum field theory. Over the course of the next year, 87 to 88, he was, of course, lecturing side by side with Friedan and Schenker and trying to understand what they were saying, and that led him to develop this important notion of a modular functor. So he talked about that at the 9th International Congress on Mathematical Physics at Swansea in July 88, and we're going to come back to that conference in just a little while. Now, there were parallel developments at the time in the constructive quantum field theory and algebraic quantum field theory community. And again, going back to that watershed Karges meeting, Jörg Froelich was there talking about this kind of subject, and Bert Schroer was there. And if you look at their contributions to the Karges proceedings, a lot of the paper is devoted to trying to make their peace with BPZ, given their upbringing in constructive and algebraic quantum field theory, which they did. But they also understood via some ideas about analytic continuation that they could construct something like chiral vertex operators. And so Nadi and I, when we referenced chiral vertex operators in our paper on naturality, this is the credit we give for the idea of chiral vertex operators. For us, it came from Tsuchi and Kaniya. Well, yes, I was there at Karges when Jörg Froelich and Bert Schroer were speaking, but I didn't get it. I just didn't understand it. But they had it, and they also considered introduce something they called an exchange algebra, which is this braiding operation. There are parallel developments in mathematics. So Jayal and Street are mathematicians, and if you look at their paper, it's called braided tensor categories, but actually they introduced the notion of braided ribbon tensor categories. And their motivations came from topology and higher category theory. And at the beginning of their paper, they talk about some of the history of their project. And the closest thing that I can see that comes to physics is that they were in part motivated by Drinfeld's famous address to the International Congress of Mathematicians in 1986 in Berkeley. So this brings me to Chern-Simons theory. Chern-Simons theory has a complicated and intricate history deserving of an entirely separate talk. And I'll just confine myself to a little bit of where I was involved and where it has to do with the story of rational conformal field theories. So at the 9th International Congress on Mathematical Physics, from the 17th to the 27th of July, 1988 in Swansea in the United Kingdom, an event of great moment took place. Atiyah and Siegel and Witten went to dinner at Annie's restaurant. It was an event of great moment because at that dinner, all the pieces for the Chern-Simons interpretation of the Jones polynomial fell into place for Witten. And then and there, he changed his talk, which was scheduled for the next day, and announced his famous interpretation of the Jones polynomial in terms of the Chern-Simons theory. This led to the third important meeting in Witten's office in D building. When he got back from Swansea, he summoned Nadia and me to his office, and I remember him explaining this. It was probably a version of his talk at Swansea. And Nadia and I were just absolutely stunned. And well, finally, that complicated formula for the S matrix in terms of the braiding matrix became clear. It was just a link invariant for two circles with representations I and J. He lost no time writing it up at the end of August 88 and the beginning of September. And at that time, I took a trip to the Soviet Union at the second half of August 1988. And I do remember going to the Gelfand seminar at Moscow University and risking my life to get there because I didn't have the proper papers, so I couldn't get in. And my host, Alexei Morozov, said, "Oh, no problem. Let's just climb over this fence." So while the guards with their AK-47s were looking the other way, we climbed the fence. And I went and I explained at the Gelfand seminar, which was quite a large audience, actually, the work I had done with Seiberg on rational conformal field theory and announced Witten's interpretation of the Jones polynomial. And Alexei Morozov also took me to Leningrad, where I went to Faddeev's Institute and again almost got arrested because I tried to enter alone without proper papers. And Alexei smoothed over the situation. And I lectured at Faddeev's Institute, again, about the same topics. I do remember I had discussions with Reshetikhin and Turayev. I remember they were working on both quantum group representation theory and three-manifold invariance, but unfortunately, I just cannot remember anything more about those discussions. I do remember an interesting aspect of the time is that John Carty, in his talk, referred to the fact that lots of Soviet scientists were not allowed to travel to the West to go to conferences and so on. Not only that, they weren't even allowed to send out their manuscripts. So when a Western scientist came to visit, lots of people would give that scientist manuscripts, scientific manuscripts, and ask them to take it back to the West and disseminate those manuscripts among their colleagues. And so I had a suitcase full of hidden manuscripts. And I do remember my terror in Moscow airport, because after all, if a border guard opened my suitcase and found those manuscripts, that border guard would not know the difference between some paper on the moduli on the measure for moduli space of genus 2 curves or something like that, and nuclear secrets. So I was terrified. And I remember the palpable sense of relief when that airplane took off. Anyway, back in the Institute for Advanced Study, Nadia and I wanted to reconcile better what was the relationship between our work and the work of Witten on the Jones polynomial and Chern-Simons theory. And that led to this paper, Taming the Conformal Zoo. And following up on a paragraph in Witten's paper, we explained how edge states naturally follow from the Chern-Simons-Witten theory on a three-manifold with boundary, which later turned out to be relevant to the fractional quantum Hall effect. And yeah, so I should say that the modern point of view actually is quite different. The modern point of view is, no, you don't derive the edge states from the Chern-Simons theory. You couple the Chern-Simons theory to a boundary conformal field theory such that the anomaly inflow makes the total system to be anomaly free. So there are all sorts of boundary field theories. The one that we derived was just the simplest one. Now, the paper also showed that all rational conformal field theories and all known methods of generating new rational conformal field theories fit very nicely into the framework of Chern-Simons-Witten theory with a compact group at some level. So that led to a natural classification conjecture. we conjectured that all chiral algebras of RCFT arise from the quantization of 3D Chern-Simons gauge theory for some compact Lie group. Now, I think if you had asked us at the time, are finite groups compact Lie groups, we probably would have said no, but of course they are. And very beautiful work by Fried and Dijkgraaf-Witten led to Chern-Simons theories for compact Lie groups. For finite groups, and that's the subject of Dijkgraaf-Witten theories, which then generalized to the important topic of pi-finite topological field theories, which is a very useful class of topological field theories discussed and studied to this day. Over the course of the academic year, many groups were trying to solve Chern-Simons theory, mostly using the method of geometric quantization. Two papers that are outstanding in that subject, to my mind, is the paper of Axelrod, Della Pietra, and Witten, and my paper with Seiberg, and we were collaborating with Shmuel Elitzer and Adam Schwimmer. And, you know, it's interesting, in the early 1980s, people started collaborations, long-distance collaborations via email. So here's just an example from my archives. By no means the first. It's actually rather late to the game. It's 1988, but it shows you what the emails looked like at the time, the SNS VAX and all of that. So that's how we were doing that. So in the summer, we lectured on all of this subject, from the mountains to the oceans. Nadi was lecturing in Banff, and I was lecturing in Trieste. And we wrote some lecture notes, which carefully describe axioms for a modular functor of Siegel, and also introduce the axiom system for a modular tensor category. These are the same as the modern axioms for a modular tensor category, expressed in terms of tensors derived from a simple set of simple objects. We say in the text that, well, we should really do it without reference to a set of simple objects, but we didn't do it. Now, they're the same. I say they're the same as the modern axioms, except we wrote a formula for S in terms of the braiding and the twist, but we then imposed the modular identities on that matrix. Now, the name modular tensor category was invented by Igor Frankl, and so I'm pretty sure that this is the first time that term appeared in print. And then Igor Frankl, speaking of memory being fallible, Igor Frankl reminded me that actually when I got to Yale a month later, we had started to do some work on simplifying the axioms, and we had even thought about imposing just that the S matrix is invertible. And from a talk I gave in fall of '89, which we'll come to in a moment, I actually mentioned this work with Igor. So we never wrote it up, unfortunately. The modern definition, which first appeared in a paper of Tarayev in '92, is that a modular tensor category is a semi-simple linear ribbon category with finitely many simple objects. And if you write the matrix S in terms of the braiding matrices, so this formula here is equivalent to the complicated formula I showed you before. If you write that S matrix, then that's non-degenerate. All you have to assume is that it's non-degenerate. And I have to say that when I heard about that result, I was actually surprised. Nadi and I were both surprised. I just totally forgotten about the work with Igor. Anyway, that's the modern definition. And it emerged from works of myself and Nadi, and Reshetikhin and Tarayev's famous papers on quantum groups and invariance of links and three manifolds, and of course, Tarayev's paper, and also work of Lyubashenko, which unfortunately I didn't have time to go track down. Now, it's interesting to look at a graph of the occurrence of modular tensor category in the abstract of published papers. Now, I looked at the Web of Science, and a reason that's a good thing to do is it has very limited coverage of mathematics. So this is actually kind of a measure of the impact in physics. What you see is actually pretty low. So there are 0 references between 1992 and 1999. I was really surprised by this graph because I would have thought that after Kitaev's observations about quantum computing, it would have started to take off around 2005, but it did not. It really took off around 2015. And the reason for that is the modern interest in generalizations of the notion of symmetry, the idea of generalized symmetries and then categorical symmetries and now non-invertible symmetries. And that movement really started with the paper of Gaiato, Kapustin, Seiberg, and Willett around 2014, 2015. Anyway, back to the Trieste lectures. Again, we were making some classification conjectures. We made a couple of conjectures, but here's one, that the modular functor of any unitary RCFT is equivalent to the modular functor of some Chern-Simons-Witten theory defined by a pair of a compact group and its level. Again, motivated by Tanakian reconstruction. Well, with the most straightforward interpretation of equivalence, the conjecture is just false. This was stressed by Konstantin Telemann in 2021 in an unpublished paper, but it's on his homepage. You can go look at it. So what is the status of this classification conjecture? Well, I think what's understood now is that the correct version of the word equivalence should be Witt equivalence. Certainly in 1989, Witt equivalence was not appreciated by me. It only came much later in physics with the existence of a topological interface in Kitaev's paper and later Kapustin and Salina. And in mathematics, the idea of tensoring with a Deligne center of a fusion category. So open questions now are, does every Witt equivalence class contain the Witten-Chern-Simons theory, Chern-Simons-Witten theory for a compact group in some level? And another question we could ask is, there's this weird thing, the Hagerup fusion category. You could take its Drinfeld center, get a modular tensor category. Is that the modular tensor category of some RCFT? So to conclude, all three steps here of the proposed classification program are very far from complete. Now I think I have till 1:30 p.m. So I have a few minutes to talk about anyons. Again, huge subject, a great topic for a full lecture on the history of anyons. Now, recently, Gerald Golden wrote an interesting historical account of the early history of the idea of particles with exotic statistics. To people like me, as postdocs at the Institute and Harvard in 86 and 87, the only thing we knew about was Frank Wilczek's paper, where he coined the term enyon. So my term at the Institute for Advanced Study ended in August 1989, and I went to Yale September 89, and the first thing I did was go to Becton Physics Laboratory because I wanted to apply modular tensor categories to enyon physics. First thing I did on arriving at Yale was go see Nick Reed. And in our first conversation, we had the Pfaffian state. And one motivation for the Pfaffian state was that the conformal blocks of the Ising model motivated us to give the Pfaffian state. And that fit nicely with ideas Nick had about pairing and condensation at the time. So our paper was written that fall. And although the idea of particles with non-abelian braiding statistics was already stated, if you look at Gerald Golden's article, you see that they certainly raised the possibility long ago. We didn't know that. So we thought we were introducing that idea. I think we were introducing the term non-abelian. We also had the idea that because a fractional quantum Hall system at long distances and low energies would be described by a topological field theory, it should be described by a modular functor or a modular tensor category. I mention that because in the condensed matter literature, that idea is usually attributed to Alexei Kitaev. That is not to disparage this paper, which is a paper of genius. And actually, Kitaev has an appendix with proper references in the appendix about modular tensor categories, which is extremely lucid, which is, I think, where most people in condensed matter actually go and learn the subject. So later that fall, I went to an important meeting, the Soviet American Workshop on String Theory at Princeton University, and I gave a talk summarizing a lot of the work I had done with Nadi on modular tensor categories and rational conformal field theories, and also summarizing this work I was doing with Igor Frenkel, which I had forgotten about. But it's there on the slides. And then part 3 of the talk was asking whether we could apply these ideas to experiment, real-world condensed matter physics. And so it was clear that a good place to do that was the fractional quantum Hall effect and the anyons via its connection with Chern-Simons-Witten theory. Interestingly, here on this slide, I'm attributing part of this idea to Froelich, Gabbiani, and Marchetti. And indeed, Jörg Froehlich's lectures at Cargès were already talking about the statistics of anyons. But for them, they were always abelian anyons. So our innovation was to include non-abelian anyons. And we did that by introducing this Pfaffian state. And we understood quite clearly that the excitations of that Pfaffian state would lead to non-abelian or anyons or non-abelions. Now, unfortunately, the reception of that talk was pretty negative. And I wish there were a video of that talk so we could see what the problems were, what I did wrong. But clearly one problem was overt hostility to the use of category theory. You see, at that meeting, some incredible new results were coming in about matrix models and two-dimensional quantum gravity. So that is a huge development from Brazan and Kazakov, Gross and Migdal, and Douglas and Schenker. And that was really the exciting thing at that conference. And people were saying, what are you doing with all this abstract nonsense, this category theory? And so there was really overt hostility to the use of category theory, which we forget because now, it's de rigueur. So for better or worse, I completely dropped this line of research and started working on matrix models of 2D gravity. Now, things were quiet. Indeed, after this, if you look at the Wikipedia article on Enyon, it says at first non-abelian anyons were generally considered a mathematical curiosity, and physicists began pushing toward their discovery when Alexei Kitaev showed that non-abelian anyons could be used to construct a topological quantum computer. So a second Kitaev paper of genius is this paper from 1997, where he made that remark. But Nick Reed reminded me, again, the faulty memory, Nick Reed reminded me that in 1992, Morph had been doing numerical experiments to show that the Pfaffian state, nowadays, the Pfaffian state is it's a very good candidate for the 5/2 fractional filling quantum Hall effect. So what about the experimental realization of non-abelions? As of today, as far as I know, it has not been achieved, but there are several encouraging experimental results that exist, especially for the existence of the Majorana edge mode. People are looking at different platforms like gallium arsenide. Bob Willett has been studying the 5/2 effect in gallium arsenide for a long time. And now also graphene and other platforms are being considered. And I would say that several groups are getting extremely close. So it will be quite interesting to see if there really are experimental realizations of these ideas of modular tensor categories. So that's the end of my story. I do want to thank all these people for helping provide relevant material and for correcting errors and reminding me of things that I had completely forgotten. So that's not all, but that's pretty much all we have time for. So thanks for your attention.
Thank you very much for your talk. Does anyone have any questions they would like to ask? I'll go first. I was wondering if you could say something more about the Pfaffian state at the time, and you were mentioning, having these experimental realizations. Do you have any concrete applications in mind, or was it more of a curiosity that you could make this generalization?
Well, again, and I do want to stress this, I simply wanted to see, I certainly did not have applications in mind, not at all. I simply, I'd been having fun with all this mathematics, but I still have some roots in physics, and I wanted to see if there were experimental implications for these ideas, especially the nonabelian statistics. So that was entirely my motivation. Now, later in 97, Kitaev made this super important remark about the relation to using topological excitations to give quantum error correction. And that certainly woke me up. I mean, after that Princeton meeting, I didn't want to have anything to do. I didn't want to have anything to do with the subject of rational conformal field theory or modular tensor categories or any of that until 1997 when I heard about Kitaev's results. And then I certainly got interested. I haven't really worked on the subject since then, but I certainly do pay attention to it now. And that started with Kitaev's paper. And he certainly had a very interesting application in mind.
I see. Thank you.
Can I ask a question? Excuse me.
Just go ahead.
Yes, Professor Moore, thank you for your insightful presentation. You mentioned the challenges of sharing manuscripts across the Iron Curtain and the early adoptions of email and other electronic, communications in academic institutions. Reflecting on these experiences, what would you say are the most significant changes in the research environment since your time as a graduate student and postdoc? Do you think these changes have positively or negatively influenced collaborative research and the progress of theoretical physics? Sorry,
okay, that sounds like an extremely interesting question, and unfortunately, the sound quality was not so good, and I couldn't completely understand it. But let me try and rephrase it and see if I understand your question, which is the impact of email and long distance communication to the development of collaboration and the progress of physics. Is that correct?
Yes,
if not, maybe somebody who could hear it more clearly could restate the question. It's a very interesting question if I understood what you're saying, but I could barely get it.
I think they were asking, yeah, I think that's what they were asking, that if you could say something about how research has changed since your time as a graduate student and how, these things have impacted theoretical physics research.
Yeah, hugely. I mean, two things. One is the improved, email and email has improved. And of course, now we have Zoom. We have this meeting right here, which would be unthinkable when I was a graduate student. And of course, also the archive. The two things have had just an incredible impact. Now, I think John Carty mentioned a little bit about some of this in his talk yesterday. So, when I was a graduate student, you would write out a manuscript, handwritten manuscript, and then you would hand it to a secretary. And of course, as a graduate student, my drafts would always go to the bottom of the pile, and they would stay at the bottom of the pile because, important professors would come in and their drafts would get put on the top of the pile. And it was very frustrating. And then there would be all sorts of errors, and then I would handwritten equations. So as John said, the advent of tech was huge. Now, another thing is, I was actually thinking of including this in the talk as sort of a window into the past, is when I looked into my files, I found these lists of names and addresses of scientists. So we used to have something like, 50 pages of names and addresses of scientists. And then we would write a paper, we would go through this list, and we put a check mark next to the scientists we thought would be interested. And then we would P-mail, a Xerox copy of our draft to those scientists, hoping that they would spread it around. And what would happen, and so when a paper came in, somebody would get a draft, and then it would go to the preprint room. So we had a room at Harvard and everywhere else. They had a room devoted to preprints. Well, guess what would happen to the most interesting preprints? They would get stolen. And so one person, some bad actor would steal the preprint for himself or herself, and then the rest of us wouldn't even have access to it. So the archive is just absolutely huge. It got rid of that problem. But now long distance, long distance communication is absolutely essential to, and has really helped with the progress of science. So you see just the beginning of that with this email, these long distance collaborations by email. So Nadi Seiberg told me that he was in Israel in '85 and was already doing long distance collaborations by email. And then, science would have been brought to a standstill in the pandemic. I mean, we could hope that everybody would be confined to their home and somebody would do an Isaac Newton and come up with something incredibly new. And when the pandemic was over, the world would change. But, well, you can hope that might or might not have happened. But instead, what did happen is people started long distance collaborations by Zoom and meetings by Zoom. So the strings meetings, the string math meetings, for a while, there were some very interesting theories, like the Western Hemisphere Colloquium on Geometry and Physics and a number of other seminars. There's still the Symmetry Seminar from Oxford. These things, I think, clearly contribute enormously to the progress of science.
Thank you so much.
I hope that
Professor.
answers your question.
Yes, yes. Thank you so much. Really good talk, by the way.
Thank you.
I was actually wondering, if you could, you mentioned again this sort of negative attitude towards category theory that other physicists had, and including yourself. Of course, it would end up being useful to your work. I was saying, could you say something about your attitude towards more abstract mathematics today, and if these experiences changed your mind? Because you had a positive experience, I guess, but then a very negative experience with the Soviet American Conference.
Yeah. Okay. I should actually, I mean, that negative attitude was from some physicists, but I mean, I think it was much less negative in the algebraic quantum field theory community. There was important work by Doppler and Roberts, for example. So I think that, it wasn't universal. There were physicists, especially in Europe, in the constructive quantum field theory and algebraic quantum field theory community, who did not have that kind of attitude towards category theory. Now, for me, I mean, I was always, from the beginning, I was very interested in abstract mathematics, and that's in the spectrum of between physics and mathematics, that's the end I've always been on. But I just, I thought category theory was nonsense. I thought, if you just work through the definitions, it all ends up being a tautology. That was my attitude. I didn't see it as a useful tool. Later, I've come to realize that was a huge mistake. And I think, and the community has as well. So certainly I remember there was a lot of negative attitudes. But now, I mean, if you look at these modern works on generalized symmetry, the categories is just their bread and butter. And not only that, higher categories. So we've moved on a lot and grown up.
Yes, thank you very much. Are there any other questions?
Oh, I have a question. More of a follow-up on one of the previous questions. Professor Moore, thank you so much for your amazing talk. I wanted to follow up on a question that was asked about the change in landscape, the research landscape. And so with the advent of platforms like arXiv, it has become much easier to disseminate work and access like a wide range of papers, but this also meant a significant increase in number of publications, and which is compounded by many young researchers feeling pressure to publish rapidly and frequently due to performance metrics and not to take risks. And one of such risks is, for example, interdisciplinary collaborations. Given that this major theme in your talk, in your view, do you think that that there is that this is a good development, if it's like a negative development?
This is a fantastic question, and this is a very, very complicated issue. So the archive is a wonderful thing for some of the reasons I mentioned, and actually for many other reasons. But it does have its dark side. And by and large, I like to think, and I could be wrong, I like to think that the archive is self-correcting, that papers that are just wrong or misguided or, ridiculously unfair tend to get forgotten. Now, I say that hesitantly because, I think there's good stuff out there that is just not getting recognized because of the sheer volume. I mean, who can read all the papers that come out every day on the archive? It's not, I don't think it's humanly possible, even within one subfield. So then we start to revert to our cliques, we'll read the papers from the people we know. So that's something we do have to be cognizant of and worry about, and we should be open to, names we've never heard of with a title that looks interesting. So that's an issue. And the pressure on young people to publish fast and to jump on the herd, well, absolutely, it's not a good thing. It's not a good thing. And the fact that important things like promotions and grants are based on thoughtless applications of publication metrics, like numbers of citations, H-index, all of that. Well, I used a publication metric in my talk. You saw it as a kind of measure of impact. And so, it's extremely tempting to do that. I do know examples where there's, and I'm not just thinking about my own work. I know examples of, where I think there are papers that are really very interesting and deep and just don't get attention. And so here are these papers. They haven't had much impact. They actually are deep. But, they're not going to lead to a promotion, or they're not going to lead to getting a grant. And so that leads to silence. So I don't know what to do about that. I don't have an answer to that because, what is an administrator supposed to do? The administrators who decide about these promotions and these grants, they can't possibly understand the huge, sprawling scientific literature. It's like this Yggdrasil tree. It keeps sprouting more and more leaves, right? And specialization. And so, centuries ago, we had natural philosophers who worked on biology and chemistry and physics and mathematics and made contributions in all of those. That's obviously not possible anymore. And there's this increasing specialization. So I don't have any good answers to that. But raising it as an issue, you were completely correct. And the pressure to jump on the bandwagon, do some trivial stuff, publish fast so that you get a lot of citations because you published on some faddish topic. that pressure is enormous. And I see it in young postdocs as a cause of great anxiety. So it's not a good thing. I think Daniel Friedan speaks very, very eloquently about very many aspects of this problem. I wish you were here to comment on this. Daniel has a lot to say about this kind of thing.
Thank you very much for your thoughtful response. It's truly an honor to hear your insights and to be here, Professor Moore.
Well, thank you.
If there aren't any other questions, we'll end the talk here.
Well, thanks for this opportunity. Thank you very much.
Thank you very much.